Welcome to Unit 7, Lesson 1. This is exponent review. So we're going to just get a little taste of what exponents are and get a good start onto that. The very first thing we want to look at is talking about which expression does not belong. Be prepared to share your reasoning. Well, here we go with mine. I'm saying the first one doesn't belong because that's the only one of these four expressions that has an exponent of 3. When we expand this one, what we would see with this is it really means 2 to the third power is saying 1 times 2 times 2 times 2. Yeah, you betcha I said times 1 because every single number out there has a greatest common factor of 1. And so the next step that we have to understand with exponents is that when we expand these exponents, we need to understand that that common factor has to be a part of that expansion because it's going to make a lot of rules in exponents make sense. So keeping in mind that this is part of the identity property of multiplication, anything times 1 is always equal to itself. We can understand with this that 1 times 2 times 2 times 2 is just simply 8 as a numerical form. Speaking of 8, you might have thought this one doesn't belong because, well, you're saying it doesn't have an exponent. I would say contrary to that, it absolutely does. It's an invisible exponent that is actually 1. And so when we think about this, what we're doing is we would get 8 by taking 1 and multiplying it by the base of 8 exactly 1 time. Similarly, like what we did here, we took the base of 2 and multiplied it by 1 3 times to give us 8. And then we see that this one simply equals 8. You may have chosen 3 to the second power as the odd one out because this is, you guessed it, 1 times 3 times 3, which is equal to 9. It's the only one of these three that does not equal to 8. And now we look at this last one, we have to think about this is 2 to the second power times 2 to the first power. So as we expand that, that's 1 times 2 times 2 times 1 times 2, which ultimately comes down to 2 times 2 times 2, which is simply 2 to the third power, or 8. And again, that's probably the only one that we said, well, it has 2 different powers there, so that one's the odd one out, and that's why it's gone. All right, that's enough of a good start there. Let's talk about this one. 2 friends, May and Andre, they found an old brass bottle that contained a magic genie. They freed that genie and it offered them each a $1 coin that's magical as thanks. Think about that coin. So they started out with that 1 coin, and then the next day, that magic coin turned into 2 coins. And then the day after that, those 2 coins, they doubled as well. They each doubled, so a total of 4 coins on that second day. And then on that third day, those 4 coins that we had above all of a sudden turned into 8 coins. And this pattern of doubling continued for 28 days. So we see day 0 when they got it, 1 day after, 2 days after, 3 days after. We have to consider what's actually happening here. Now, May tried to calculate how many coins she would have and then remembered it instead of writing 1 times 2 times 2 times 2 times 2 times 2 times. Really long time, right? For any number of coins on the 6th day, she should have just written 2 to the 6th power. And the reason we say 2 to the 6th power is because 2 as the base represents that coin that is doubling. So that doubling pattern is represented in the base. And we could say to the nth power, where we would say let n be any number of days. And what this would describe is a pattern of doubling any number of days. So then we have to ask the question, is the number of coins May had on the 28th day is very, very large. We would write an expression to represent this number without computing its value. We would say, well, that coin is doubling for any number of days. We're looking at the 28th day. It would be the 28th day. There you go. We didn't have to calculate anything. We didn't have to compute anything. All we had to do is figure out what doubling meant and how many times would that double. I could sit there and write this out and say 1 coin times 2 times 2 times 2, doubling every day. but I really don't want to express it that way because 2 to the 28th power would make a whole lot more sense. I'm really curious about something, so I'm just going to go back to this. 2 to the 28th power, that's a lot of coins, right? So I could sit there and put this into my calculator and just say 2 times 2 times 2 times 2 times 2 times, right, over and over and over again. That's just going to be a really long time. Or I guess you couldn't even see what I was doing, but I could sit there and say 2 times 2 times 2. And it's just, you could tell it's going to get ridiculous doing that 28 times. So if I take my phone, turn it horizontally, I get this little setup like this. And then it's really hard to read. I'm sorry, I can't get this to focus any better. But when we see that focus, we're looking for a little button right here that has X to the Y power. At least this is where it's at on mine. You're looking for this button that looks like that. Perhaps on your calculator, it might say Y to the X. Or if you don't see any of these ones, you're going to look for a caret button, or you'll look for one that has X and then a shaded in box. Those are the most common ones that I have seen. And what you're going to do is you're going to push the number 2, then you'll press that special button, then you'll press 28, and then you'll hit equals, and you're going to get a great big number. Let's just see how big. 2 raised to the 28th power is, holy moly, 268,435,456. So $268,435,456 just in 28 days. That'd be an amazing coin to have. So let's think about what happens next. We got this guy over here, her buddy Andre, right? Poor Andre. Here's the sad news. Andre's coin lost his magic, all of them, after the 25th day. So May has a lot more coins than he does. How many more coins does May have than Andre? So May had 2 to the 28th power, and Andre has 2 to the 25th power. And so what we want to look at there is 2 to the 25th power is 2 raised to the 25th power is a much smaller number. So it's 33 million, right? But still, it's not all that million, all that big. Here's what we want to take a look at is this. These 4 words right here. How many times more? That is a golden phrase right there that means divide the quantities. It simply means divide or division. So when I look at that division, I can take this and I can say 2 to the 28th power divided by 2 to the 25th power. So I'll just do that. 2 to the 28th power divided by 2 to the 25th power is equal to 8. So that divided by that equals 8. In a later lesson, we're going to learn a little shortcut for this division that we don't have to use a calculator for. And we say how many more times coins does May have? In this case, May has 8 times more coins than Andre. Okay, no big deal. If you want to go and see what that looks like, go ahead and go back to here. There's kind of a cool interactive piece where you can go ahead and type in that web address or scan that QR code. And what you'll see is a picture of those coins following this pattern, doubling every day for 14 days. It doesn't go up to 28 days. So let's talk about this broken coin. What happens if I have a broken coin, one that just quit working? So we have another friend, Jada. Jada picks up one of those coins that seems different from the others. And she notices that on the next day, only half of that coin is left. That's kind of creepy. So that first day, she's got a whole coin. The second day, she has half of a coin. So it cuts and it makes it half of the size. And then let's bring this over just a little bit closer to this other stuff. So that's day 1, she's got a whole coin. Day 2, she's got that whole coin has become half of a coin. Day 3, that whole coin has cut in half again, making it 1/4 of a coin. And then on the third day, 1/8 of the coin remains. So that means again that it's cutting in half. Following this pattern again, and equals 1/8. So what fraction would happen after 6 days? Well, what we notice here is that our repeating pattern, talking about a half of it, is that now our base is 1/2. Really, really important thing to remember is that anytime we have a fraction and that we're going to be taking times powers, we need to put that fraction inside of parentheses. And so what fraction of the coin remains on 6 days or after 6 days? We would say 1/2 of the coin for any number of days for 6 days. And our rule for this whole situation is what would happen just to continue that working. I would say that my coin is diminishing or decaying by 1/2 every single day for any number of days, where n again represents the number of days, and so I can simply substitute n for 6 to find out 6 days. And what fraction of the coin remains after 28 days? Well, without finding its computational value, we would have 1/2 of that coin for 28 days. Write an expression to describe this without computing its value. That'd get pretty small. What fraction of the coin remains after 28 days? That's going to be, I really want to put this in here without describing it, but it's 2 to the 28th power. And just because I think it's pretty funny, that coin is now 1/300. What was it? Let me look back here. 268 million. Let's see here. 435. 456. That's what's actually left of the coin after 28 days of just cutting in half and in half and half and half and half again. What we're really looking for on this one is what fraction of the coin remains after 28 days. It'd be 1/2 to the 28th power. That's how we write that expression describing it without computing its value. But I just took it a few steps further, and that would be the actual fractional value. And you're saying, well, no way, that's impossible. So you're telling me that that coin could disappear completely? The answer is no. Not mathematically. Mathematically speaking, if so, after how many days, it's actually impossible. It is impossible to constantly, actually not constantly, let's say this, to find a quotient of 0 when dividing by 2. There's no value out there that I could divide 2 by or divide by 2 to get 0. It's just not going to happen. So with this case, theoretically, what we'd say is that it could continue dividing in half over and over and over and over and over again and never actually stop. When we think about that on a physical side or metaphysical side, we would have to consider that at some point we would be down to a subatomic level, which means the particles are so small that they would actually cease to exist in some fashion. So for all intents and purposes, though, we would consider this that multiplying by a power of 1/2, dividing by 2 over and over again, we can actually never get to 0. So the coin can never truly, totally disappear. For this next one, I want you to think about something. This is a family tree. We have our friend named Tyler. Tyler has 2 parents, a mother and a father. We're going to draw a family tree for Tyler, showing his parents and his grandparents and his great-grandparents. So here's his parents. His mother also would have had a mother and a father, and the father would have had a mother and a father to make grandparents. And those grandparents would have also each had a mother and a father, and a mother and a father, and you get the point, right? Okay, so there's Tyler's family tree. What's really interesting is Tyler, just a few generations back, this is what we would consider 3 generations back, 1, 2, and 3 generations back, has several relatives. We say that Tyler's 8 great-grandparents, so those 8 people that were represented there as mothers and fathers, are 3 generations back from Tyler. At which generation does Tyler have 262,000 144 ancestors. Well, what we just saw is that we saw Tyler was the product of two people. So we had one kid times two people, which was the first generation. Each generation after that was doubling. Again, we went from 1 to 2 to 4 to 8. So how many times would this pattern have to continue until it equals 262,144? Give it a try. Give me the answer in here as a power of 2, and then describe that. I want you to think about this for a minute. I'm going to get a little philosophical on you for a second. If you think about this, this isn't too far back. Every single one of us came from 262,144 ancestors. That means we have a pretty long legacy that we should be able to respect. So I would tell you, in order, respect yourself enough to make good decisions and do the best that you can. Respect your parents because they're part of that line and you represent, they're part of that line that represents your legacy. And your legacy represents a whole bunch of people that you may not have realized actually existed. So understanding these numbers helps us understand how many people have truly been on this earth and how interconnected we really can be. So the whole thing that we're after with this is exponents. They make writing really big numbers a lot easier. We show that they're repeated multiplication. So for example, the one thing I don't like here is that they didn't show 1 as the common factor. An advantage to writing 2 to the 6th power is we can see right away that 2 is this 2 to the 6th power. We can see it right away by seeing 2 times itself 6 times, or 2 times 1 6 times. When this is written out using multiplication, we need to count the number of factors. Imagine writing out 2 to the 100th power using multiplication. I'm not going to do that. 2 times 2 times 2. 2 to the 100th power makes a whole lot more sense. So let's say you start out with 1 grain of rice, and every single day the number of grains of rice you have doubles. So on day 1 you have 2, day 2 you have, or on day 2 you have 4, day 4 3, so on day 3 you have 8, 4 you have 16, so on and so forth. When we write 2 to the 25th power, we can see that the expression that the rice has doubled 25 times. So when we talk about doubling 25 times, we're saying that we're doubling 1 times 2 25 times. So that one piece of rice has doubled 25 times. And so we just simply, rather than writing as 1 times 2 to the 25th power, by the identity property, we just recognize it as 2 to the 25th power. That is a whole bunch of rice, more than a cubic meter, meaning that it would fill up a whole box bigger than a cubic meter. So welcome to that introduction of exponents. We're going to do a whole lot more with exponents. Make sure you do a good job on your homework. Remember to ask any questions if you got them. And don't forget to have a great day.